The dark matter, which is this bread and butter of this mysterious mass in the universe, and the dark energy, which is pervading everywhere and we have no idea, we think are related.
Dark dimensions, F theory, and what lies beyond space-time. Kamran Vafa, professor of science at Harvard, whose doctoral advisor was Edward Witten, proposes a revolutionary idea that could either unify or break decades of physics research. His theory suggests dark matter and dark energy, comprising 95% of our universe, might be manifestations of the same underlying phenomenon. Come with me into the heart of the universe, both observable and not, where the nature of the cosmos hangs in the balance. Professor Vafa, welcome.
Thank you.
I want to know what got you into math and physics.
Well, when I was a child, from the very elementary schools, I remember loving math. So math was always part of my excitement about intellectual excitement. But physics kind of gradually got into it in the sense that I started looking around things like looking at the moon. And I remember I was second grade when I was wondering why the moon isn't falling down on the earth. And what I found amazing was that it didn't bother people around me, that fact that there's something up there like kind of suspended. And it's kind of like, I don't know how to put my finger on it. It didn't seem to intellectually bother them to want to know the answer to it. So these kind of things from the beginning kind of attracted me to nature and understanding how it works. That gradually became my excitement about physics as a whole and fundamental physics later on. And luckily for me, my interest in math and physics matched in terms of the requirement of the activity. So I'm very happy that I'm in this field now.
Would you say that your love for math is greater than your love for physics now, or vice versa?
I think to me, math and physics are inseparable, actually. I mean, the way for me, my thinking of mathematics is in terms of objects and things. It's physical. So for me, math is part of physics. And to me, even though math has its own language and you can apply it to many things, nothing to do with physics, for me, it comes to life through physical objects. So to me, math and physics are not separate.
Contrast that for me for one of your colleagues who may be a mathematician who doesn't view math in a physical manner. How do they think?
Of course, you have to ask them. I'm not saying everybody should view it the way I do, obviously. I'm saying that's, to me, math is something not so different from physics. In fact, when I want to really feel what the math is telling me, I imagine physical objects or physical things and what it encapsulates. So to me, math and physics can be a good relation in terms of enhancing one another. So, of course, math can have its existence independently of physics, and physics kind of orthogonal, not completely from math, but to me, as the way I look at them, is they are not separable.
Have you ever talked to any of your colleagues who are just mathematicians and asked them, okay, how is it that you're thinking about this problem? And then you were able to see that, hey, actually, there's something that if you're a physicist, you would be able to discern this phenomenon more easily, or maybe the opposite, you would be misguided because of your physical intuition, and they're not.
Well, we often discuss with mathematicians, for example, joint collaborations. So I am sometimes in the situation you just mentioned, where I have to explain why this idea that to a mathematician might sound strange or unmotivated, or why this result should hold, is very natural from a physical perspective, and try to explain why. So yeah, this happens quite often, and that's the excitement of it. Namely, things which are unintuitive from a mathematical perspective becomes intuitive only from the physical perspective. Of course, there's sometimes the reverse. That is, things that are from a mathematician's perspective natural, from physical perspective may look unnatural. So that's why, to me, trying to view these as a unified thing is actually helpful. And I try to view them as two different parts of the same thing.
Just as the Mariana Trench plunges to depths of 11,000 meters, concealing ecosystems we've barely glimpsed, our universe harbors its own vast, unexplored realms. Marine scientists estimate that we've mapped less than 20% of the ocean floor, and cosmologists face an even more daunting challenge. Roughly 95% of the universe's energy mass content eludes our understanding. The cosmic abyss isn't composed of water or rock, but rather what physicists call dark matter and dark energy. Their gravitational effects shape galaxies and accelerate the universe's expansion, yet they remain invisible to our most sophisticated detectors.
Can you give an example for math where it seemed unmotivated, but it seemed natural coming from physics other than mirror symmetry? And then for the opposite, where it seems unnatural in physics, but is highly motivated in math, and it ended up being correct?
Things that in math, they're not motivated from physics. There's a huge number of them. The question is whether you want it technical or non-technical or whatnot. To me, mirror symmetry that you kind of disarmed me with is actually the most beautiful example of that.
Well, the reason is that that's the most common example, common in our circles.
Well, I think I probably should explain that because I was at the center of that circle, so I should explain what happened actually in that interaction.
Sure.
So I was explaining to my colleague Yao, who was my colleague here at math department, the fact that from physics it seems natural. This was before we conjectured mirror symmetry, that there should be as many Calabi-Yaos as positive Euler characteristic as negative one for Calabi-Yau threefold, which is a prediction of mirror symmetry. And he kind of found it very odd that we were saying something like this. And he asked, why are you thinking this way? I said, well, from a physical perspective, it's natural because there's no natural definition of the sign of this operator, and you can choose either sign. There's no canon, there's no God-given choice. Therefore, different choices give you the opposite choices. And so therefore, from physics, reconstructing geometry will land in one or the other Calabi. You cannot distinguish which one. He said, well, that doesn't sound too right to me because we know more of negative Euler characteristic Calabi than positive. So there's no symmetry from the known example. So despite that, we conjectured it. So it wasn't like something was unintuitive. Something was against the mathematical evidence.
Right.
And nevertheless, we were so sure of it, we conjectured in my paper with Wolfgang Lerche and Nick Warner.
Yes.
So that's an example. And that later on, we had no non-trivial example other than six-dimensional tori. So non-trivial examples came later. The trivial example existed, but non-trivial ones wasn't there. But our motivation was basically simple examples and the general idea. But this happens again and again. So the things that fit together in some particular way in different physical ideas motivate a way of thinking which comes to a mathematical statement, which might sound strange to a mathematician at first, and now it's not.
Can you give one more example?
So examples of kind of math that a mathematician finds interesting or not. I mean, there are different kinds of things that mathematicians might find exotic. For example, let me go back to let me say it before. It depends on whether you're interested in the content which is mathematical or the content which is physical. I will give you the surprising physical content, which to a mathematician sounds strange. So if you explain to a mathematician that algebra or groups can explain why time dilates or length contracts, as Einstein's theory of relativity shows, special relativity, they find no connection between, simple group of this and that, and this amazing fact that, lengths contract and time dilates. For them, that physical reality does not connect with that other fact they know about, the group theory of transformations, which we call Lorentz group. So they understand one piece of it, but why that means the other one for them is a total mind-boggling thing. So if you try to say, no, this means that, and how does it mean that, and what does it imply, and what else it could mean, and so on, is shocking. And so, therefore, it depends on how you want to kind of package it. Is it physically exciting, mathematically exciting, or other ones? But mathematical excitements, there are many examples. Other ones are, for example, mathematicians are interested in counting curves. Counting by curves, I mean how surfaces fit in some geometries. It's very hard for them to do that. Mirror symmetry was one way to actually do this. But regardless of mirror symmetry, we found, again, from a yet different physical reasoning, that the way these numbers are working conspire in a particular way to give you certain rational numbers. Even though you're counting, they manifest themselves into a non-trivial rational number. This is something that my colleague Rajesh Gopakumar and myself found, how to unpack these rational numbers to decipher integer quantities out of them. So we told our mathematical colleagues that if you compute this rational number that they knew how to in principle formulate, and if you do this operation on them, you can extract some integers out, which actually are counting some things. And for them, it was shocking. And they said, how, why, where is that coming from? Again, that came from understanding of these objects from physical terms. So there are many examples like this. Another example has to do with aspects of gauge theories. So we were interested with Witten in studying instantons for four manifolds. So this involves studying very non-trivial questions of geometry of bundles, gauge bundles or connections on which admit self-dual and considering self-dual gauge connections on them. And we were interested in computing on these spaces, the space of these instantons, their Euler characteristic. And again, from a physical reasoning, we knew that, or we were expecting that if you stack them up, instanton number 1, 2, 3, 4, they form a function. And this whole function has amazing properties, what's called modular transformation properties. So we told mathematical colleagues that we are looking for this structure and we don't know whether these numbers are computable or not. And they were surprised that we are even looking for such a structure. And the first few examples that we found along these lines were already shocking. And now the math community, there's a lot of research trying to understand these invariants that we defined in my work with Witten. So there are many examples like this, and I can go on, but I do not know whether that's within the range of interest of your listeners.
You just mentioned some invariant. What was its name?
This is, they call it now the Vafa-Witten invariants, but it is the invariants having to do with four manifold and instantons on them.
Yes. Also, when you're referring to invariants, the one about rational numbers, counting them, that's called the Gromov-Witten invariants, if I'm not mistaken. Please explain, what are the Gromov-Witten invariants?
Gromov-Witten, actually, I should have said it. The rational numbers I was telling you is the Gromov-Witten invariants. So what we learned with, what we suggested with Gopal Kumar was how to unpack these rational numbers, the Gromov-Witten invariants, into integers, which is now called the Gopal Kumar Vafa invariants. That repackaging of that rational numbers in terms of integers was something that was surprising for mathematicians, and that's what we found.
You mentioned that there are self-dual connections, and I'm unsure, why is it that self-dual or anti-self-dual connections are so important? And is it only important in 4 dimensions?
Well, there are similar things in different dimensions, but the 4-dimensional one, the self-dual connections are most interesting in 4 dimensions because the notion is really makes sense only in 4 dimensions. The dual of a gauge, the curvature of a gauge bundle is 2-form only in 4 dimensions. So therefore it makes sense to say it's self-dual or not, only in 4 dimensions. The reason they are interesting is that they give you critical points of Yang-Mills theory, the minimum energy configurations in a given sector. So for each given sector, you can ask so first of all, the space of gauge connections on a manifold splits into different spaces. In each one, you can ask what is the minimum energy configuration, or in physical language, what is the minimal action configuration? And they end up being self-dual ones. So it's like a ground state of the gauge connection in that sector. Of course, in the trivial sector, the ground state means you turn off everything, gauge field is 0, nothing.
Yes.
But in the other sectors, you have to turn them on, and the self-dual ones are the ground state. So they basically are the ground states of each configuration of the gauge connections. So having studying the ground states in each topological sector is, of course, natural.
Okay, so physics can be seen as a history of revolutions. I remember you mentioned this once, and one of the revolutions is that the constancy of the speed of light, or the Earth is not the center, or the solar system is not the center even. And then you said that the next revolution was, well, among others, but one of them is that point particles may not be points, they may be extended objects, aka string theory. Now, do you see there being another revolution that needs to occur within string theory itself?
Oh, it has to, because our understanding of string theory is certainly incomplete. We do not have we just have pieces of what the theory is, not the full formulation of it. So yes, of course, there's got to be a better formulation of this theory. We have, I would say that what we have learned is the analog of the wave mechanics. Before we had we had pieces of wave mechanics like de Broglie had for quantum mechanics without having Schrödinger equation. So I think we are not there yet.
String theory promised a unified, so-called theory of everything, but its landscape has proven far more rugged than physicists have anticipated. Some hail it as our best shot at understanding the universe, and others dismiss it as untestable speculation, better relegated to the funding bodies of mathematics, not physics.
Well, obviously, if you knew the answer, you would be publishing on it, but you probably have some hunches. So what do you feel like is the assumption in string theory that may be overturned shortly?
Well, overturned is not I don't think we have something which is in the form of a laws of like Maxwell's laws that you can say this can be wrong or this can be right. String theory is a collection of examples of consistent solutions to quantum gravity. Those are not going to be overturned because we have checked all about them and they make sense. What we don't have is a unifying framework of what brings this whole thing together. So it's not something to be overturned, but something to be developed. I would say it's not that. It's like saying that how do you just to say the other way? Suppose you want to say how would you overturn de Broglie's wave statement? You don't overturn it. You basically develop it. You develop it to quantum mechanics. That's what string theory is right now.
I see. So of all the papers that you've worked on, Professor, what do you feel like is the one you're most proud of?
It's hard to say. I think I enjoy every paper I write. You could say not all of them with equal love, but I think overall it's not as easy as say I like this paper and not the rest, or this is my top one and not the rest. It's not like that. I think one thing that is perhaps it's not quite appreciated by non-scientists is that it's not just one paper which does anything. One paper might be a summary of many other papers that you have done or thought about. Mm-hmm. And you might kind of summarize or get the aha moment in one paper. That's true. But it didn't come in vacuum. And that fact is, I think, sometimes missed. You think, this is the great paper. No. This is built upon a lot of laborious other papers which don't get much recognition. And so I have the same feeling about my own works, that some of them are just building up towards the crescendo, and suddenly one paper, if I'm happy with, it's because of those other works, which may say, who cares about that paper? But those are the beginning of the thinking. So I would not want to encourage that culture of thinking that there's this paper I like.
Speaking of crescendos, sir, there's F theory, and I understand you may not consider it the crescendo of your work. Maybe you're working on something else, but why don't you tell us what's exciting that you're working on currently?
There are other directions that I find equally interesting, or maybe even more aspects having to do with engineering quantum field theories from string theory. How do you get them from string theory, or engineering black holes from string theory? Again, I find very interesting, or understanding aspects of topological strings from string theory. What do they mean? These mirror symmetry, another example. All of these I find equally exciting, and not a single thing. Like F theory for me is one thing. I wouldn't say, actually right now I'm working on a very different area of string theory, which I can talk about it later with you, but called the Swampland program, which is now what I'm most excited about. So there are parallel, there are many things which kind of interrelate and have interconnections. It's not one thing that determines my excitement about the subject.
Okay, so F theory has multiple time dimensions, and we're going to get to that, but I want you to first outline what are some of the issues why people historically didn't consider there to be more than one time dimension.
F theory suggests that there are two extra dimensions in the game in some hidden form, but that existence of these two extra dimensions is not clarified in what form, and it's not necessary for using this framework. So there's this thing called the F theory framework, where you can use that to construct solutions to string theory. That's a robust statement, and it does not include extra time or anything else. In my paper, when I wrote the first idea about the F theory, I also suggested that these two extra dimensions that are hidden in some form, there's more naturally have one space and one time direction. And that's why the notion of two times came in. It wasn't necessary for my discussion. So the idea that the F theory has made the fame for having two time directions, that's actually kind of irrelevant for the discussion. The F theory construction really does not require extra time dimensions.
So it's two directions that are extra, that are unspecified. They could be two spatial, they could be two time, a total of 3 time dimensions. It could be, but it doesn't actually matter.
It could be, one, and my suggestion is one space and one time, which means two altogether, two times. Yes, exactly. So it's not, since that time, that space does not directly enter the discussion. It's just an it's kind of like a partial hidden aspect of the constructions, as if there's 2 extra dimensions.
Would there be something other than space and time that it could be? So that is to say, we look into these 2 blocks, that it could be a space one, it could be a time one. We don't know where to put the blocks.
Well, since it's not formulated in a way that has a physical properties of the rest of the space and time, it certainly is not of the usual type. So yes, whatever it is, it's not of the usual space and time. That's part of it, because we know how the usual space and time looks like, and these are not one of those. So there should be something a little different about these two if they are in some sense physical.
And what makes them different?
Well, the symmetries. They don't have the symmetries to make them part of it. You cannot rotate our space to that space. So the rotation of our spatial direction to these extra dimensions doesn't make sense. So the theory does not allow that. So therefore, it's not part of it.
Earlier, when asking about F-theory and how it may or may not be the crescendo of your work, and you outlined quite a few different directions like the swampland and black holes, can you please pick one of them? Pick one of those topics. Let's say the swampland. Let's just talk about the swampland. Why is it that the swampland has you so fired up right now?
Well, swampland is for me exciting because it's the executive summary of all I have learned from string theory. If somebody told you, okay, you have studied string theory, tell me what did you learn? What it is that this quantum gravity is all about, this is what Swampland is trying to do. It's exactly the lessons we are supposed to have learned from studying string theory. Now, what does that exactly entail? Quantum gravity is very different from the rest of quantum field theories. So if you take particles like quantum quarks and electrons and how they interact in the context of gauge theories, we have beautiful theories which describe them very nicely. Quantum chromodynamics describes the theory of strong interactions. Quantum electrodynamics does the same for electricity. And there's the electroweak force, which is another kind of gauge force, which also does as equally a good job for describing the weak forces. Naively, one might have thought the gravity is of the same type. You can take the gravity and do the same thing you do with these other forces, and that just doesn't work. And part of the reason it doesn't work is that a lot of the notions of quantum field theory breaks down when it comes to gravity. Quantum field theory has a hierarchical structure in terms of short and large distance physics. And the idea is that you're always interested in large distance. What happens at large distance, not at microscopic scale. So you kind of integrate out what we say, or basically average out what's happening at short distances to come up with an effective description at larger distances. Sometimes we call this the effective field theory perspective about how things are emerging. This idea works beautifully in quantum field theories. Namely, you start with a given large distance physics and ask what kind of symmetries are operative at that scale. And using symmetry arguments, you can more or less write down what the physical action looks like. Except that you don't need to know what was the short distance physics leading to this theory. So you just ignore it because it's not relevant for your question. So we learned the fact that if you're interested in describing large distance, by and large, you can forget what's going on at short distance. And that is why quantum field theory has become so powerful, because you can just take symmetries and write whatever you want, and at a larger scale, deal with it. Even if you don't know the details at short distance, that does not affect your calculation at large distances. Very powerful idea. This idea totally fails for quantum gravity. The idea of separation of scales of short and large, microscopic and macroscopic, is what doesn't work for quantum gravity. And the idea why it doesn't work is one could kind of see why. So let's do the Gedanken experiment. Like, you want to describe what happens at short distances. What we do in particle physics is to take two particles and accelerate them toward each other with ever higher energies. Why? Because when they go at higher energies, they can probe shorter and shorter distances. The distance scale you probe is inversely proportional to the energy in the center of mass of such a collision. So therefore, you go at a higher and higher energy, you collide them to see what's going on at shorter distances, namely what comes out of such a process of scattering these particles, what is created gives you a hint about what's happening at higher and higher energy scales or shorter and shorter distance scales. This is the idea of quantum field theory. If you try to do this for quantum gravity, this begins to work the same way that we think about quantum field theory. You take energies of the particles to go higher and higher until you go to such high energies that something totally unexpected happens. What happens is that instead of particles coming out, suddenly nothing comes out. So you hit them at a very high energy, and what happens instead is that you create a big black hole.
Yes.
A black hole is a solution to Einstein's equation, which is described by long-distance physics, not short-distance physics. So you are interested in understanding what's going on in short distance, and the physics told you, sorry, you cannot go any further than this. After this scale, everything is becoming bigger. So higher and higher energies is now translating to higher and higher distances, which is opposite to the way of thinking that we had. In other words, high energy and low energy kind of are connected. This discussion of separating the short and large distances in this way fails. So the idea of the effective field theory fails in quantum gravity precisely because of black holes. So the black holes run the show in this case. So this is why quantum gravity is very special. Now I come to Swampland. So this was just a background about the connection between quantum gravity and why is it so different from quantum field theory. So you say, okay, so okay, they are related. So but what does this relation really mean? How do you actually use this fact? What is the description? This means that you cannot just say, I have this and this symmetry in long distances, write down for me the action. That you cannot expect to work. String theory tells you that in fact does not work. In other words, if you just studied with the symmetries, you would have thought about the many, many, many more possibilities than you can actually get from quantum gravity. The short distance physics tells you not all of the things that you thought are okay are actually okay. There's a conspiracy between that short distance and large distance, which is not apparent to a field theorist point of view. How do we know this? String theory. So the examples that we have learned from string theory tells us that the things that we get, no matter how we change. So in the string theory, we choose these extra dimensional geometries because string theory is more than 4-dimensional space-time. These extra dimensions have their own geometries that we can pick. Calabi-Yau, this manifold, that manifold, G2 manifold, spin 7 manifold, whatever. You choose it and you see what physics comes out. You change the manifold, changes the physics. So you say, okay, I want to see a different physics. I want to get this kind of physics. Can you give it to me? The answer is almost always no. The kind of physics you get are very, very restrictive. In fact, among the set of all possible conceivable physical theories that you may have been interested in getting, the ones that you actually get are measure zero. The ratio of what you can get to what you want to get, or you could have wanted to get, is zero. That means it's basically minuscule possibilities of what are actually consistent theories with gravity. So our perspective of what is this fails. Now,
wait, is that a theorem?
Well, we have a lot of evidence. No, there's a lot of evidence for what I just told you. And so in different examples, it's a theorem. Depends on how precise a question you want to ask. So I'll give you a few examples of this. To try to understand what are these restrictions is what we call the Swampland program. Swampland program tells you out of these possibilities, which ones are not good. Swampland. Now, the other ones are good. The ones which are not bad, we call them landscape. So you might say, why are we looking for swampland instead of landscape, which is what the good ones are? The point is that the landscape are measure zero. So it's like saying you have points on a plane and you want to find these points. Well, good luck. What you can more easily say is, well, you draw a line and say to the left, there are points, to the right, there are none. Much easier to do that than to say there is a point exactly there. So Swampland program is trying to find these lines, kind of ideas like to the left is okay, to the right is bad, and this and that. So this narrows what is possible. It doesn't pick you those points because those are very difficult because they're very rare. So that's the Swampland program, is to understand these lines. And I will try to tell you some of these lines or these Swampland criteria that we have found over the years. So the first one, which actually happened even before the Swampland program started even back in the, 40s or 50s, 1940s or 50s by Wheeler and collaborators, which is the statement that no quantum theory of gravity has symmetries other than gauge symmetries. In other words, you cannot have symmetries in quantum gravity without having electrical field associated with them. Like in our universe, we have, of course, electric charge, which is conserved, but that has electrical field with it. So what this statement is that you could not have a universe where there's electric charges with no electrical field coming out of it, and the charges are still conserved. That is a no-no. That's not possible. Now, from the viewpoint of an effective field theorist like you and I, it sounds perfectly fine. Why not? Why can't you have objects you can count but has no electrical field on it? Says quantum gravity says, no, you cannot. So this is almost at the status of a theorem. Why do we think so? Well, because we have ideas having to do with black holes, which tells you that if this was not the case, you would get into trouble because you can send one of these charges to the black hole and black hole evaporates and you get rid of that charge. So therefore you violate the conservation of charge. So symmetries disappear through the black hole evaporation process. And so there are arguments like that. So when you say, can you prove it? Of course, it presupposes we have a framework or principles to prove, but we don't have those. So I cannot tell you I can prove it because I don't have the Euclidean principles like the axioms of Euclid or whatnot. So I cannot give you such a proof. But to the extent that we believe the evaporation of black holes works the way we do, which we are very sure of, this is a proof that there is no global symmetries. Another example is weak gravity conjectures that we have, which we have a huge amount of evidence, which says in any conceivable quantum theory of gravity, gravity is always the weakest force. It's not just in our universe. You could not have had any consistent theory of physics for which gravity was not weaker than other forces. That sounds, again, strange from a viewpoint of effective field theories because you can imagine having two electrons.
So the hierarchy problem is then the hierarchy inevitability?
No, the hierarchy is more specific question. Hierarchy just says, why is the scale so much smaller? It could have been just a factor of 10 smaller.
Oh, I see. Okay.
Hierarchy says, why is a factor of 10 to the 19 or 10 to the whatever smaller? That's a different one. Here, we're just saying the scale is lower, but we didn't say how much lower. But it goes in the direction of making hierarchy possible, let's say. It goes in that direction, but it doesn't tell you have to have a huge hierarchy. So this idea, the weak gravity conjecture, if you think about it, it's a little strange why it's true. Because if you imagine you have two electrons, well, if you put them at a distance r relative to each other, there's a repulsion between them, which Coulomb taught us. It goes like a square of their charge divided by distance squared. Mm-hmm. Like we call E squared over R squared, the distance squared. But there's also a gravitational attraction between them, which goes like their mass times mass over R squared. That's Newton's gravitational attraction. So it goes like M squared R squared. So gravitational attraction is M squared R squared. Electrical repulsion is E squared R squared. And we are saying repulsion always wins. In other words, M is always smaller than E. Well, you could have imagined that electron's mass was much higher and it would have been the other way. But we say, no, the theory of gravity would not have worked. You see, that's a positive surprise because you would have thought there's no reason a priori the mass of the electron has anything to do with its charge. This says, no, it better be smaller than its charge in the appropriate units and in the fundamental units in physics. So these kind of ideas, and these are just two examples. There are many more examples.
Yes.
Perhaps I will say one more example because it's also one of the most remarkable examples, which relates to duality symmetries of string theory. This statement, which I find probably the most difficult to see from an effective field theory predictions or perspective, is what is called the distance conjecture or duality conjecture. The statement is that if you take parameters in your theory, first of all the parameters in your theory are dynamical. Now, what does that mean? That means when we usually think about constants of nature or numbers and so on, we're saying there's no such thing in physics. That means that things that we think are constants or numbers actually can be changed. They're dynamical. You can change them in one region of space to be bigger or smaller. It's not in fixed numbers.
Okay, so constants become fields.
Constants become fields, or more precisely, the expectation value of certain fields.
Right. Okay. Even the speed of light.
Speed of light we view it in fundamental units as one, so we don't even talk about it. It's not a speed of light. We view it as one. It's not changing for any discussion that I'm working. In other words, speed of light is not a. Let me make it more clear. So in your theory, you don't need to have a parameter for speed of light. That just sets the units for us.
So something else will change, but that will change with respect to the speed of light.
Yeah, you could try to do that, but all the parameters in the theory will be somehow related to fields. Now, if you take so now I haven't stated what distance conjecture or duality conjecture is. It tells you that if you take this field and take the value of this field to extreme values, small or large, that means in your physical theory, it might have been a coupling becomes extremely small or extremely large, something like that. Your theory always breaks down. Always. That's a surprise. That means the extreme limits means something breaks down.
Yes.
Now, what do I mean by breakdown? It means that if you go to far away corners of these extreme parameters, you get a tower of particles which used to be very heavy, becoming lighter, 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 and lighter. And as you go to extreme values, these give you an infinite tower of light particles. Very, very little mass, separated from each other by little masses. And so you have a huge number of particles that you had ignored because back in the middle of the field space, they were very massive. So you could have ignored them. Mm-hmm. But when you go into these extreme parameters, they become so light, you cannot ignore them. And if you try to incorporate them one by one, you cannot succeed because there are infinitely many of them. So therefore, if you go far away to the left or to the right or anywhere, any direction you go, your description breaks down. So what happens? A new description comes over and takes over, incorporating those degrees of freedom, which is not your original description at all. It might mean that some dimensions opened up. It might mean that some extra particles or strings are in the game that you had completely no idea about. This gives us what we call the dual description. So the duality in physics, I just explained to you in a language of this form, is of this form. You start somewhere, you go one limit, you find one description, which is what we call one duality frame. If you go the other direction, you get a completely different perspective, another duality frame. So these physics between them are describing the same physics, but at different extreme regions of parameter space. So this is the duality or distance conjecture, which is also another example. And this does not have to be true without gravity. It's only there if you have gravity. Uh-huh. So quantum gravity changes the whole rule. The rules of quantum field theory are not applicable. And that's, I think, the most exciting thing we have learned in string theory. String theory tells you that the paradigm that the particle physicists had been operating for 100 years is badly wrong, because they thought they could ignore the short distance away from large distance. We have learned that you cannot decouple them. The short and large are intricately connected when it comes to gravity. And this is crucial because potentially a lot of the puzzles of particle physics, like hierarchy problem, like all these puzzles that particle physics has difficulty with, that try to use supersymmetry to answer, for example, and it didn't work. So many of these puzzles, which doesn't look natural to a particle physicist, is because they had ignored gravity in the discussion. And the reason they ignored gravity was kind of benign. They said, look, gravity is a weak force. It is not strong until you get to Planck energies. And we are not, in our accelerators, we are nowhere near Planck energies. So forget about that. So we're just talking about other particles. Forget about gravity. They thought that not thinking about them is perfectly fine because the energy that we are doing is not related to that. They were not thinking about the connection I told you about black hole. The higher energy and low energy are intricately linked with each other. And that picture is what is, I think, at the root of failure of particle physics to try to explain a lot of these fine-tuning or hierarchies that appear.
Are particle physicists still thinking that we don't have to incorporate gravity?
There's a group, it's beginning to change. So, and I do know that there's a number of particle physicists are now becoming cognizant of this fact. For example, my colleague here, Matt Rees, is an example of such a group of particle physicists who appreciate the importance of the quantum gravity as being in the mix to get insights into particle physics questions. So there is growing, but still, by and large, I think the majority of particle physicists, unfortunately, are not as much familiar with this. And so it's gradually getting to them. But I think it will get, because it's kind of, it actually gives their field of vitality to make predictive powers, because, as I just told you, the number of possible allowed ones are measure zero. So therefore, this gives you predictive power. So if you understand what these rules are,
yes,
it will give you what particle physicists like, because they are looking for such paradigms. So I think they will, when they get to learn a bit more about it, I think they will appreciate it even more.
So in other words, usually in a treasure map, you have X marks the spot, but we don't have the X. If we had the X, we'd have the answer. But if you can exclude parts of the map, slowly, ever more, so you encroach on just what is the viable region, then you say, okay, so we don't have to dig across the whole Earth. We can just dig in this guy's back alley in Panama.
Exactly. And so sometimes what happens is that you get lucky. Like, the thing is, the X is on the left of this line, but the experiment finds it very close to this line, and you didn't know whether it's going to, finds it very much along a line here somewhere, and you do not know whether it's going to be past this or not. And you say, no, it cannot be past that. But the experiment says that it cannot be so much to the left either. So therefore, you're kind of stuck on that line or very close to it. So in this way, it becomes predictive. Even though it sounds like you're just excluding something, combined with experiments, it actually can become predictive. And that's what we have been using it for.
So while the Swampland has a negative connotation to its name, it's actually positive because you want to be able to exclude more and more so that you could dig at a place that less than... Okay. So when you use the word consistent earlier, when you say that, look, we're excluding what's inconsistent. Inconsistent means what?
Inconsistent means it does not have a short distance completion. That means it looks fine at large distances, but there's no full theory which you can have answer to questions like what happens at high energy scatterings. It will have answers to some region, but not the rest. So it doesn't fit together. So you don't have a complete picture. It doesn't work.
Okay, because the way mathematicians use the word consistent or inconsistent is that if you have a theory that's inconsistent, you can predict everything because you have A and not A at the same time. But that's not the sense that physicists mean inconsistent when they're speaking about this theory of quantum gravity is inconsistent.
No, it is the same. It means that suppose I give you a theory for which you study the scattering of particles at some energy E, and it looks perfectly fine and everything is good, but you don't know how to compute when E is very large. And somebody says, no, the E that you picked, if you try to do that at large energy, it gives you nonsensical answers. The answer blows up or it becomes zero or something which doesn't make any sense. Therefore, you say, well, that means that your other one is wrong. So A and not A also in that sense means if you thought this A, then you're saying the other one is wrong. So in other words, you get one side or the other not working. So if you wanted the way it works at long distance, the short distance doesn't work. So it is something like A and not A at the same time.
I see that as unintuitive, but I don't see that as inconsistent. So if someone predicts infinity, I don't see that as being inconsistent. I see that as being not corresponding to our world, but mathematically, I don't see that as being inconsistent. Can you help me out?
No. I'm not explaining. I'm not perhaps explaining myself clearly to you. So suppose you have drawn a line and you draw a straight line. Suppose you draw. I'm just giving a boring example.
Sure.
You're drawing a straight line, and for physical reasons, suppose this is something that has to be positive, like a mass of a particle or something. You're drawing as a function of parameter a straight line. And this mass the particle should have a positive mass everywhere. But you have studied it far away along the real line, and you find that as you change this parameter, linearly grows with that parameter. You say, good, I'm done. The mass of the particle goes linearly, it's finished. And then somebody comes and tells you, no, it's not finished. If you go to the other regime, it's negative mass. It doesn't make any sense. That's what I'm saying. So the thing that you thought is fine, it doesn't work on the other side.
In that example, the difficulty is that you said, for physical reasons in the beginning, you prefaced this with, for physical reasons, we have to assume the mass is positive. So
no,
that's
not
what
physical
I'm getting
reasons.
at.
No, not physical reasons. I mean, I'm just saying, suppose in your physical theory, you come up with a physical theory which says, oh, mass grows linearly and in this regime is positive and that's worked perfectly fine, you're done. For some regime of parameters.
Yeah.
And your theory doesn't tell you anything about the other regime, but your prediction is that it should be linear.
Yes.
But then somebody comes and tells you that cannot be because of the silly fact that if you take this and continue to negative, the mass will become negative and that's not allowed. And that's all. And therefore, that simple fact that in this, I'm giving a little bit of a silly example so that I can illustrate the point. In one regime, you know how to do a computation and you think it's fine, but actually fails because you're not looking at the totality of the question. So it's inconsistent as a whole. So it ends up inconsistent. So one side is like large distance physics and the other one is like a short distance physics. If you take something at large distance physics and you study it, you may not know that you're assuming something about short distance which is not allowed.
Okay, now is that because the short distance comprises the long distance or vice versa?
No, they are connected. They are connected. You see, I was trying to give you the black hole example. You could not have ignored it. You couldn't say they're independent.
I see.
They're connected because the higher and higher energy gives you bigger and bigger distances. So they're somehow related. What you thought that you're probing at short distance actually ends up being large distance. Higher energy knows about large distance, not short distance. So what happened there? So that paradigm was wrong that one was using. So that's what has, so it's a revolutionary, in some sense, really revolutionary. That is, the ideas that we thought about scales, short and large separation, is actually badly wrong. And it is actually, in some sense, a good development because that leads to predictive power for us.
Well, let me see if I understand by taking your silly example and making it even more silly. So let's take this cup and let's say, look, this cup must comprise, if you were to zoom in, elements that have mass because this guy as a whole has mass. But if you keep zooming in and your theory then tells you that there's negative mass there, well, the way that you get the total mass of this cup is by integrating. So you should get something that's negative mass. However, you have the observation that has positive mass. So there's an inconsistency there. Would that be correct?
Yes.
Okay, so let's talk about classical versus quantum. Is the notion of classical versus quantum fundamental? And if not, then why not?
No, it's not fundamental. Classical and quantum can be interchanged, and that mirror symmetry is an example of it. So something which appears classical to one perspective can be quantum to another perspective. Because the analog of Planck constant can itself be a parameter. And if you go to very strong, large values of that Planck, then as the duality example I was telling you about gives you some other description opening up. So sometimes that becomes a classical picture of somebody else. So something which is highly quantum to one perspective becomes classical to another. It's a part of duality example.
Professor, what would you say is the definition of string theory? Let me preface this. So in other words, if someone hands you a theory, how do you know this is a string theory? Is it that it has extended objects? Is it as simple as that?
No, I wouldn't say that way. I would say string theory attempts to describe consistent quantum gravity theories. String theory has landed on what we think might be the only constant theory of quantum gravity. But in the Swampland program that I'm studying, for example, does not assume that. So we are open to the possibility that there are other constant theory of quantum gravities. But we have all the evidence. In other words, what I mean by that is that we don't want to say just because string theory cannot give you this physical reality, that cannot be obtained, period. We try to see if you cannot rule out a physical reality by some other reasonings, like black hole physics, beyond string theory, which is nothing to do with string theory per se, which rules that theory out or not. So string theory could be therefore, in some sense, be derived if everything that is allowed ends up being what you can get in string theory. If the totality of what is allowed is exactly equal to what string theory gives you, then string theory is the only game in town. But we are not assuming that. And in fact, I think it's healthy not to assume that. We want to assume quantum theory of gravity. So consistency of a quantum theory of gravity. That means gravity is well defined with the properties involving black holes, with other particles, with the consistent set of rules of scatterings and objects and all that. So we have a set of rules that we can check whether they are consistent, and that's what I mean by quantum gravity being good. If you handed me one of those, I would start asking questions like scatter this, do that, do this, to see if it's consistent. And maybe in some regime, I see some extended objects because that's one of the things that I expect. And then maybe a string, maybe a membrane, maybe something else. So therefore, these are the tests I will run this object or theory that you give me about. So string theory by now, I think is, I would say, at least to me and many of my colleagues, convincingly, perhaps possibly the only theory of quantum gravity, but it's always, I think, good to be open-minded in possibilities of other possible theories that could exist. I think it's also, if you even want to understand just string theory, having this perspective is good because it tells you what are the fundamental things in string theory? What makes string theory tick? What are the basic reasons or ideas that go into it? So you have to step back away from string theory to try to get that formulation.
What are some of the other theories that may compete with string theory to describe our universe that you feel like perhaps you don't feel like they're on the right track? Otherwise, you would switch gears and just start publishing it.
I don't think there's anything comparable to. I mean, you hear sometimes loop quantum gravity and this and that. I think it's just far off about what we are talking about. So I wouldn't say even on par. So So yeah, I don't think right now there's any game in town other than string theory, but I think we should keep it open-minded. Not that we have found one, but I'm just saying the possibility of having some other structure that's consistent with gravity, we should be open to it. But right now, I think all the evidence is pointing towards that. For example, in the context of Swampland, we are finding that the rules that seem to be consistency of black hole physics, unitarity, evaporation, all the things that we think should be true regardless of whether it's string theory, when you use them, you narrow the space of theories down, and you find a lot of the cases that we know how to narrow them down, you end up to be exactly the same set you get in string theory. And so that, to us, begins to smell like, okay, that's the only game in town. So we are now deriving pieces of it. So with enough supersymmetry, with high enough dimensions, we actually have accomplished that we can actually push this to a classification of possible things, and it exactly matches what string theory gives you. So we are very happy with the fact that now we are finally beginning to quote unquote derive string theory from some first principles.
Practically speaking, what would it mean to keep one's mind open about other quantum theories of gravity or other unifications of gravity with a standard model? Like, does that mean a grant body for like an additional grant body or additional department? Like, practically speaking, what is meant?
No. I will tell you how it will appear. Suppose I'm studying possible consistent theories of scattering of gravitons. And I study them and I find some framework. I become so smart. I manage to exactly solve what are the allowed possibilities. And I find there are only two possibilities in 10 dimensions. One of them gives you exactly the answer in string theory. And the other one is not. But it looks perfectly consistent. Okay? That other thing is whatever you want to call it. It's not string theory, therefore. And so, therefore, we would have found another theory. So if we were there. But more and more, the way we are doing it, we're always being narrowed down only to the one corner, which is what I recognize, which is string theory. Not in everything we have done that, but in high enough supersymmetry with high enough dimensions, we are being cornered to the string corner. And so this is what we call the string lamppost principle. Sometimes the people told us, well, you guys are studying only string theory and you might be suffering from the lamppost effect. That is, you're only seeing things string theory gives you. But if everything that we're getting is part of that lamppost, that is everything. That's what we are finding. And this thing we are calling the string lamppost principle. That is, there is nothing else other than the lamppost of strings.
When people talk about quantum gravity and you go to different lectures, there's often, well, what we do is we sum over the geometries, like you sum over different paths in the Feynman integral. Is that the correct approach to quantum gravity? You sum over the different possible metrics?
At some level, it seems perfectly okay, but not at fundamental level. I don't think we do have a fundamental definition of quantum gravity. At large distances, it might be like that you take pieces. But if you come to a short distance like Planck's scale, I don't think that's the correct description. At distances for which the space-time geometry itself is a highly bubbly quantum form of geometries bubbling off and so on, I don't think you should think about it as summing over geometries, because the notion of geometry doesn't make sense. So you're in a regime where geometry is not even a good approximation. So therefore, I think in some regimes it might be that, but not as a whole. I don't think the notion of distance and metric is universally makes sense.
Help me with this, because one way that I wasn't able to ever square why summing the possible metrics is a viable option is because in order to define a fermion, you have to define a section of a spin bundle, which if you need a spin bundle, you need the orthonormal frame bundle, and that requires a metric in and of itself. So if we're varying the metric, then I don't know what it means to define a fermion. That hasn't sat right with me.
Well, first of all, there are different things that you can think about fermions. Fermion you can define by a local transformation of space. Now, local does not necessarily mean Planckian distance. You can take a piece of your space large enough for which you can describe the notion of geometry, and then you can, in that notion, describe the notion of fermion you do a rotation and you see if the fermion picks up a sign or not. So that's, you find out how does it transform on the rotation. That's only the notion in which there is a geometry. Otherwise, the fermion does not exist separate from geometries. It exists at a given point in your space and time. So to the extent that your space-time is bad, your notion of fermion might also become bad. So you can only so you're self-consistent. In the regime for which you have a geometry, then you can define a fermion perhaps, or other objects living on it. If that object that doesn't live anymore, then what? Then you should not be able to define that fermion the way you used to do. It should be a completely different way of doing whatever it is, depending on what is the object that replaces it.
You know, earlier you were saying, look, there are different gauge fields for electricity, magnetism, and the weak force and the strong force, and some people want to incorporate gravity like that. So what is meant when people want to incorporate gravity in a similar manner? People say gauge gravity, quote unquote gauge gravity. What does that mean?
No, gravity is gauging diffeomorphism symmetry. So diffeomorphism is a symmetry of a manifold. Diffeomorphism means that you can choose any coordinate system. And gravity gauges it. It means that that symmetry should be respected locally. You can take your coordinates and change them different places, different ways. That's what we mean in physics when we say we gauge it. So a mathematician would just say that, oh, all you're saying is that the local coordinate charts in different ones are independently chosen. Yeah, that's all I mean. Your physics should be independent of that.
So in Yang-Mills, when we gauge, we say that there's SU3 cross SU2 cross U1, and then that's like a principal fiber bundle, and G is that group. So are you saying that to gauge gravity, you still take as the base manifold M, but then you gauge, like you put fibers of the diffeomorphism group?
Well, yeah. So what I'm saying is the tangent bundle of the manifold is canonical. You don't give it anymore. You don't choose the analog of G because the manifold is there, the tangent space is fixed. So that's different. For gravity, just as another difference with gauge forces, the gauge forces you artificially have to with another structure, like a principal bundle.
Yes.
A group. Manifold, no. Because once you give me a Riemannian manifold, you have given everything you need to give me. So for the geometry of that space is itself the metric. Namely, that's what it is. So you don't need to say anything. Of course, you could say, oh, you're talking about tangent bundle. Yeah, you can think of it that way if you want. Metric is a structure on tangent bundle, connection on tangent bundle, and so forth.
What is your superpower?
What does that mean?
So what I mean is that Witten explicitly said that his superpower isn't mathematical prowess, though he has that.
Oh.
What it is deciding on what problems to work on. What do you see as your secret sauce? What makes Vafa Vafa?
Well, trusting my intuition, I think. And trusting my intuition over formalism. I don't trust formalism, I trust my intuition. So my intuition might clash with formalism, and then I'll go with my intuition, not the formalism. So I think that's what, if there's anything different, is that. And so if my intuition goes against conventional wisdom, I'm not afraid of stating it. Mirror symmetry is an example of that.
How do you decide what problems to work on? Is it just intuition?
Intuition. I cannot explain what makes me think one is better than the other, but my intuition guides me.
What if we've been chasing a ghost? For decades, dark matter has been physics' elusive quarry, invisible, yet supposedly everywhere. It's the cosmic glue holding galaxies together. Or so we thought. What if Qamrun Vafa is correct? What if dark matter doesn't exist as we imagine it? Vafa's theory hinges on the cosmological constant, the energy density of empty space. In anti-de Sitter space, with a negative cosmological constant, this energy is attractive, just like gravity. In the universe that we inhabit, it's a de Sitter space that is repulsive, driving cosmic expansion. Vafa proposes that what we call dark matter and dark energy are manifestations of the same phenomenon tied to the nature of de Sitter space itself. This unification arises from string theory's Swampland conjectures, which suggest that not all effective field theories can be consistently coupled to gravity. Specifically, Vafa is explaining that the apparent fine-tuning of the cosmological constant is teaching us about the dark sector of the universe.
And what is it that you're working on now?
Swampland principles. So understanding this. So to me, as I said, right now I have been starting the idea around 2005, this Swampland program, and ever increasing number of physicists, especially a young crowd, are actually working on this. So it's become a very active community of physicists trying to decipher what we have learned from string theory. You see, I think you ultimately want to say, what does string theory have to do with the real world? And I think a lot of the efforts in string theory, even though they are interesting, they seem to be going away from connecting to the real world. And I think trying to reshape back, focus back our attention from principles of we have learned about string theory to the real world is what I find exciting. And surprisingly, you can do this, and that's what we are beginning to do. And so some of these ideas about the swampland we have actually now used to make a very bold prediction, which is potentially observable in the next few years. And so I will try to explain where this bold prediction comes from. So I told you about when you take extreme parameters in your theory, you always end up with getting a tower of light particles.
Yes.
Well, you could have asked me, really? I know an extreme parameter. Tell me what does it correspond to, namely dark energy. The dark energy in fundamental units of physics is 10 to the minus 122. It's so small. It's extreme. Okay, what is your tower? You see, this question it just sounds like a benign question. Like, am I claiming there's extreme? Okay, it's extreme. This is extreme. Tell me what's happening here. Just that way of reasoning pushed us to a direction which suggested that, yes, there must be a light tower in our universe. And that light tower we identify with dark matter. So in other words, the dark matter, which is this bread and butter of this mysterious mass in the universe, and the dark energy, which is pervading everywhere and we have no idea, we think are related.
Mm-hmm.
It is the extremeness applied to dark energy, or this distance or duality conjecture, which suggests there must be a tower. Now, you could say, what is this tower? Where is this tower? How do you actually, what is the mass scale? How do you see it? So combining this general idea I told you with other observations, it turns out there's only one possibility. The possibility is that there's one of the dimensions of the microscopic dimensions are actually bigger than the rest. And of the scale dictated by dark energy, and that energy scale amounts to about a micron, 1,000th of a millimeter. So we are saying that there must be one of these dimensions bigger than the rest, of the order of 1,000th of a millimeter, a micron. And but our universe, the 3 plus 1 dimensional space-time, which we are living in terms of electrons, quarks, and all that, are in a hyperplane in this higher dimension. So you imagine you have one higher dimension, but we are on a hypersurface on that, stuck on that, and the size of that is about a micron. So we got this from just applying the Swampland principle. The distance conjecture, which I try to explain why it's so natural from the physics perspective, because the duality of string theory demands it. So if you just tipped it and say, okay, let me assume without knowing exactly how I get my universe from string theory, just that idea, what does it imply? You immediately get these kind of predictions, and the micron scale size of this extra dimension is actually observable potentially in our universe, because they have gone up to 30 microns and they haven't seen it. So how do they see it? Well, they put two particles and they measure the force between them. If the force goes like 1 over r squared, then you're in 3 dimensions.
Yes.
If it goes like 1 over r cubed, then you're in 4-dimensional space. So you have grown a space dimension. So they want to see if the force becomes stronger.
The force of
gravity. Of gravity. So I'm saying that the Newton's gravitational force law being 1 over r squared becomes stronger at for higher dimensions. But if the extra dimension has a micron scale, and if you are separated more than a micron scale, you won't feel the extra dimension. It looks like 3-dimensional. But if you bring it closer so that you can feel the extra dimension, if you're within less than a micron.
Yeah, that's super interesting. One of the questions that I had was going to be, look, is there something about the extra dimensions of string theory that necessitate compactifying to something extremely small? And you're saying, no, this is relatively large. No, it's a micron, but that's relatively large.
This is extremely large in some sense, surprisingly. And I'm saying this is not that the string theory forces you. This is observation combined with the Swampland idea. So in other words, we are, as I explained, sometimes you have an idea that, okay, you should not be to the left or to the right of this line, etc. That's like the distance conjecture, that if you go for large distance in the field space, you hit a tower of light particles. But then you say, oh, but I know in our universe, lambda is blah and blah. What does that imply? Then you can use this. So it doesn't tell you lambda or the cosmological constant had to be small. But if it is small, then you can use it.
And would this say that dark matter is several particles? It's not just a single one? It's a tower of them?
Well, so the tower that I'm talking about turns out to be one particle, namely just graviton. Now you might say, wait a second, graviton is massless. But 3 plus 1 dimensional graviton is massless, but 4 plus 1 dimensional graviton is not massless, because the graviton can have waves, oscillations in the other direction. This tower I'm talking about is nothing but oscillations of graviton. So it unifies gravity with dark matter. So dark matter is nothing but excitations of the graviton, which is why it's weakly interacting, because gravity is weakly interacting. So the dark matter becomes the tower of these graviton, which is weakly interacting anyhow. So it unifies dark matter with graviton and dark energy into one package.
Does this then have a name, like a separate
Dark
theory?
dimension. We call this dark dimension scenario. Yes. So dark dimension scenario is a scenario that there's one extra dimension opening up. And this is coming from this Swampland idea I just told you. So there are a few other predictions that this makes about cosmology, in particular about axion physics and other things that are potentially also very interesting. And ultimately, it's an answer to a kind of an answer to a question that Dirac was asking. Dirac had noticed that different scales in physics has bizarre relations by factors of 10 to the 30, 10 to the 20, 10 to the 40, these big numbers. And he was saying, it looks like they are not related by factors of 2 or 3. They are related like by powers. What is the reason for this? So in the context of Swampland, we have actually seen exactly the reasoning for why they are powers. And more than that, we find things are given by powers of 1/12 of the cosmological constant. So things come in chunks of lambda to the 1/12.
Huh.
And that's about 10 to the minus 10. So you get 10 to the minus 10, 10 to the minus 20, 10 to the minus 30, etc. And these give you the different scales in physics. One of them gives you the higher dimensional Planck scale. The other one gives you the weak scale. Another one gives you the neutrino scale. Another one gives you the large scale of physics, the large size of the universe. So all of these scales fit into this hierarchical fashion given by the dark energy. So the dark energy gives you a unifying principle about all these different scales.
This dark dimension theory, when did it occur to you and your collaborators? Like, how long was the time span?
It gradually developed. So the distance conjecture was started around 2006.
Okay.
The fact that you go, but then we applied the distance conjecture to the case of cosmological constants in another paper. I think that was 2018. And then in a few years past, we tried to think about cosmological aspects of it. And then we gradually were going in the direction, and in the 2022, it led to the actual say, why not? Combining this gives you that. So the idea came gradually, but it could have been done much faster.
What do you think about de Sitter quantum gravity?
Well, quantum gravity, de Sitter seems to have a problem of stability. And so a lot of these ideas in the context of Swampland seem to point towards the idea that de Sitter space with positive energy cannot be stable. Well, the question would be, okay, if they are not stable, what's the time scale of the instability? And what we think is that the time scale of the instability is itself set by de Sitter. That means it's what we call the Hubble scale. So, for example, if you take that in our universe, it suggests that the scale in which the universe will unwind, or the dark energy will unwind, is roughly the age of the universe, current universe. So that is kind of interesting because it will tell you that the dark energy has a time scale associated with it also. And we don't know if the recent observation of DESI, which the dark energy survey, which tried to see whether dark energy is constant or not, they seem to have some indication that dark energy is actually changing and decreasing with time in the same kind of time scale as one would naively think about along the lines I'm talking about. So these kind of ideas tell you that dark energy is actually dynamical and actually evolving potentially in time. It's certainly not stable. So quantum gravity of de Sitter should not exist in the sense of a complete de Sitter. It could be just patches, short time maybe, but not in the long term. In the long term, it will decay.
So does that mean that our universe, which is de Sitter, will decay?
Yes. Correct. We expect our universe not to be stable. In fact, I think every string theorist believes that we just don't know exactly the time scale. The arguments emanating from Swampland suggest that the time scale is given by the Hubble, which is roughly the age of the current universe. So that's the kind of a time scale.
You're saying that the age of the universe is the expected age of a de Sitter universe to collapse.
Up to a log factor, which I didn't tell you about. So in other words, it's age up to a logarithmic correction. So if you want to get the upper bound, we think it's like 2 or 3 trillion years.
Okay.
So it's upper bound. We don't think it's going to be more than 2 or 3 trillion years. This is an idea from Swampland, which has less of an evidence because we don't have examples of de Sitter from string theory. So we have extrapolated what we know to get this. It's what's called the Transplanckian censorship conjecture. So this is one of the things that we are trying to gather more evidence for. Mm-hmm. Check it to see if it's correct, if it's not correct, and so on. But the idea suggests that there's this upper bound. But at any rate, all the examples we know in the context of string theory, which has dark energy, is always unstable. The question is whether how unstable they are, and that's what we are trying to figure out.
Why did you call that a problem? Because when I asked, just to reiterate, when I asked, okay, what do you think about de Sitter quantum gravity? You said the problem is that it's unstable. Why is that a problem?
Yeah, because de Sitter, when people talk about de Sitter, they mean everlasting de Sitter. If you're just having a piece of de Sitter, then that's different. So in other words, there's a time. De Sitter has a time axis.
Okay.
So if you take the curvature or the scale of de Sitter and extrapolate in time, we're saying it won't last. So therefore, it's not de Sitter. You call it de Sitter or not, it becomes ambiguous.
So, Professor, to end, I want to know, what is a mystery that you think about on a daily basis?
Well, trying to see what we can find theoretically to check this idea of dark dimension right now. These days, I'm mostly consumed about trying to understand how we can confront string theory with reality. I'm hoping that in my lifetime, there will be experiments which will hopefully show us how string theory works in real world.
Yes, you said that many of your colleagues, not all of them, but many of them may have gone too abstract or gone too in the way of forgetting about this universe, and you're trying to bring them back with the Swampland program or the weak gravity conjecture in particular. So can you expand more on that? What is this delineation between people who don't have a tether on physical reality, though they think they're studying physics? It's called theoretical physics.
No. I wouldn't say they don't have tether on physical reality. I think they think we don't have enough tools to study physical reality. I think they're under that impression. They think that's unapproachable right now with our techniques. So let's do abstract stuff for which our techniques might apply. That's their mindset. And I disagree with that mentality. I think we do have a number of ideas and techniques which does apply to our universe, and that's our difference. Otherwise, I don't think they're untethered to reality. They are. They just don't think that we do have enough of the tools.
So it's like a jigsaw puzzle, and you feel like we have the pieces already to put it together.
They say, don't waste it. We don't have. Exactly. That's the right way of saying it. I think we have enough of the jigsaw pieces in the place to figure out some of the rest that are crucial.
And last question. At what time did we have enough of these pieces of the jigsaw? Like, what was the last piece that you're like, okay, from this point, we had enough to infer? If we were only clever enough, I mean, we have more mathematical tools now, but physically speaking, the experimental results were enough to allow us to infer the rest of the picture.
Well, the dark dimension is when I got convinced that we may have a chance, because that was a scale which was coming from the relation of dark energy with a particular physical scale that we can actually see in our universe, was motivated by abstract principles of string theory. So this connection that one thing leads to this concrete thing, like, wow, of course there's a very extremely tuned parameter in our universe, the dark energy. Why don't we even apply it? It was kind of daring to say, well, there's a tower. Where is that tower? Nobody saw this tower. And suddenly you remember that in two problems always come together. Problems come in pairs. And the two problems were, one is, what is dark matter? And the other was, what does this tower have to do with anything?
Yes, that's super interesting to me, because dark matter and dark energy were always misnomers to me, because they don't a priori have anything to do with one another. But then in the popular press, they said they're both dark, and so most people think there's some association, but you're actually concretizing that.
Yes, we are saying they are related. They are unified into one object, into this dark dimension. The existence of this large length, micron scale length, relatively large, is the manifestation of dark energy. And the long wavelength of gravitons on them is the dark matter. So the tower of light dark matter gets related to the size, which is set by the dark energy. So dark energy and dark matter get related. The mass of the dark matter gets pegged to the value of dark energy.
Well, Professor, I'm going to leave the set of papers on this subject by you and your collaborators on screen right now and in the description for people who want to find out more. Thank you for spending so much time with me.
Thank you. Thank you for interviewing. Have a good time.
Firstly, thank you for watching. Thank you for listening. There's now a website, curtjaimungal.org, and that has a mailing list. The reason being that large platforms like YouTube, like Patreon, they can disable you for whatever reason, whenever they like. That's just part of the terms of service. Now, a direct mailing list ensures that I have an untrammeled communication with you. Plus, soon I'll be releasing a one-page PDF of my top 10 toes. It's not as Quentin Tarantino as it sounds like. Secondly, if you haven't subscribed or clicked that like button, now is the time to do so. Why? Because each subscribe Each like helps YouTube push this content to more people like yourself. Plus, it helps out Curt directly, aka me. I also found out last year that external links count plenty toward the algorithm, which means that whenever you share on Twitter, say on Facebook or even on Reddit, etc., it shows YouTube, hey, people are talking about this content outside of YouTube, which in turn greatly aids the distribution on YouTube. Thirdly, there's a remarkably active Discord and subreddit for Theories of Everything, where people explicate toes, they disagree respectfully about theories, and build as a community our own toe. Links to both are in the description. Fourthly, you should know this podcast is on iTunes, it's on Spotify, it's on all of the audio platforms. All you have to do is type in Theories of Everything and you'll find it. Personally, I gained from rewatching lectures and podcasts. I also read in the comments that, hey, toe listeners also gain from replaying. So how about instead you re-listen on those platforms like iTunes, Spotify, Google Podcasts, whichever podcast catcher you use. And finally, if you'd like to support more conversations like this, more content like this, then do consider visiting patreon.com/Curt Jaimungal and donating with whatever you like. There's also PayPal, there's also crypto, there's also just joining on YouTube. Again, keep in mind, it's support from the sponsors and you that allow me to work on Toe full time. You also get early access to ad-free episodes, whether it's audio or video. It's audio in the case of Patreon, video in the case of YouTube. For instance, this episode that you're listening to right now was released a few days earlier. Every dollar helps far more than you think. Either way, your viewership is generosity enough. Thank you so much.